Ever wondered how UV visible spectroscopy plays a crucial role in scientific research? Well, wonder no more. Welcome to our journey into the world of spectroscopy, where we'll be exploring the invisible rays that have a visible impact in our daily lives. UV visible spectroscopy is a cornerstone technique in the world of analytical chemistry, used extensively in laboratories worldwide. It's a method that allows us to study and analyze the interaction of ultraviolet and visible light with matter. This interaction provides us with valuable information about the chemical and physical properties of the substances we are studying. But why is this technique so important? It's simple. UV visible spectroscopy allows us to identify unknown substances, determine the concentration of compounds in a solution, and even examine the structural aspects of molecules. It's like a detective tool for scientists, helping them unravel the mysteries of the microscopic world. In the next few minutes, we'll be taking a deep dive into the theory of UV visible spectroscopy. We'll explore the principles of the Beer-Lambert's law and its deviations, the concept of photometry and spectrophotometry, and the Woodward rule. We'll also delve into the instrumentation of UV visible spectroscopy, discussing single-beam and double-beam spectrophotometers and the optimum conditions for spectrophotometric measurements. We'll then shift our focus to the various analysis methods in spectroscopy, including single and multi-component analysis methods, derivative spectrophotometry, and spectrophotometric titration. And of course, we'll discuss the myriad of applications where UV visible spectroscopy comes into play. This exciting journey is not just about understanding a scientific method, but also about appreciating how this technique shapes our understanding of the world around us. So, fasten your seatbelts as we embark on this fascinating exploration of light, matter, and the interactions in between. Stay tuned as we delve into the theory behind this fascinating technique. Let's dive into the theory behind UV visible spectroscopy and Beer-Lambert's law. UV visible spectroscopy is a technique based on the absorption of ultraviolet or visible light by a substance. The amount of light absorbed is directly proportional to the concentration of the substance, which is the essence of Beer-Lambert's law. This law states that the absorbance of a solution is directly proportional to its concentration and the path length of the light. It's a foundational principle in spectrophotometry, the quantitative study of electromagnetic spectra. However, remember that Beer-Lambert's law is not without its limitations. It assumes that the molecules are not interacting with each other and that the environment is constant. These assumptions may not always hold true, leading to deviations in results. Nevertheless, this law provides a solid grounding to UV visible spectroscopy. Understanding the theory is just the beginning. Let's explore more. Ever heard of the Woodward rule and photometry in the context of UV visible spectroscopy? Well, the Woodward rule helps us determine the maximum wavelength of absorption, or lambda max, of a compound based on its structure. It's a fascinating piece of chemistry trivia that provides a rough estimate of where certain functional groups will absorb light in the UV visible spectrum. On the other hand, photometry is all about the intensity of light. In UV visible spectroscopy, we use photometric measurements to quantify the amount of light absorbed or transmitted by a sample. It's an essential component, as it allows us to determine the concentration of a particular component in a sample by comparing the light intensity before and after it passes through the sample. Both the Woodward rule and photometry play pivotal roles in UV visible spectroscopy, providing essential insights into the nature and concentration of substances. With these fundamentals clear, let's move on to the instrumentation. The right instruments and optimum conditions are key for spectrophotometric measurements. Imagine a pianist. To perform at their best, they need a well-tuned piano and a serene, quiet environment. Similarly, for spectrophotometric measurements, we need the right instruments and ideal conditions. Let's delve into the world of single-beam and double-beam UV visible spectrophotometers. In a single-beam spectrophotometer, the same beam of light serves two purposes. It acts as both the reference beam and the sample beam. This type of spectrophotometer is simple, affordable, and ideal for routine analysis. Now let's talk about double-beam spectrophotometers. These sophisticated devices have two types, the sequential type and the simultaneous type. The sequential type uses two separate light paths for the reference and sample beams, which are measured one after the other. On the other hand, the simultaneous type splits the light into two beams that pass through the sample and reference cells concurrently. Double-beam spectrophotometers offer higher accuracy, precision, and are perfect for complex analyses. Now let's shift gears and discuss the optimum conditions for spectrophotometric measurements. The first condition is maintaining a constant temperature. Temperature variations can affect the absorbance of the sample, leading to inaccurate results. The second condition is the use of clean, scratch-free cuvettes. Any impurities or scratches can cause scattering of light, which can distort the measurements. The third condition is the proper alignment of the instrument. Misalignment can lead to errors in measurements. Lastly, the sample itself must be prepared optimally. The solution should be clear, free of bubbles, and the concentration should be appropriate to prevent saturation or too low absorbance. So there you have it. The right instruments, be it a single beam or a double beam spectrophotometer, coupled with optimum conditions, are the backbone of accurate spectrophotometric measurements. With the right tools and conditions, we can now explore the methods of analysis. Ready to learn about the different methods of analysis and derivative spectrophotometry? Let's dive in. Single and multi-component analysis methods form the backbone of spectrophotometry. Single component analysis, as the name suggests, involves the study of a single component within a mixture. It's like trying to find a specific voice in a crowded room. Once you know what to listen for, it becomes easier to isolate and understand. On the other hand, multi-component analysis is a bit more complex. It's the simultaneous measurement of multiple components within a mixture. This is akin to trying to discern multiple voices in that same crowded room. It requires a certain level of finesse and understanding of the individual components to tell them apart. Now, let's turn our attention to derivative spectrophotometry. This technique is a bit like the detective of the spectrophotometry world. It's all about uncovering hidden details and nuances that may be missed by other methods. Derivative spectrophotometry involves taking the derivative of the absorption spectrum. This can help to resolve overlapping spectral bands, making it easier to identify and quantify different components within a mixture. In simple terms, if the absorption spectrum is a landscape, then the derivative spectrum is like a topographical map. It provides a more detailed view, revealing the peaks and valleys that might otherwise go unnoticed. This is particularly useful when dealing with complex mixtures, where components may be present in minute quantities or have similar absorption characteristics. The beauty of derivative spectrophotometry lies in its sensitivity and precision. It allows for a more accurate quantification of components, even in the presence of noise or spectral overlap. It's a powerful tool in the analytical scientist's arsenal, capable of providing insights that might otherwise remain hidden. Now that we've discussed the methods, let's look at a practical application: spectrophotometric titration. Stay tuned, because the world of spectrophotometry has even more to offer. Spectrophotometric titration is a fascinating application of UV visible spectroscopy. As we delve into this topic, let's first clear up what it entails. Spectrophotometric titration is a method where we monitor the titration process with the help of a spectrophotometer. This device measures the amount of light that a sample absorbs. By doing so, we can determine the concentration of the substance we're interested in. Now let's imagine we're titrating a solution of a colored substance. As we add the titrant, the color of the solution gradually changes. This change in color corresponds to a change in absorbance, which the spectrophotometer detects. By plotting the change in absorbance against the volume of titrant added, we can determine the end point of the titration. This method is particularly useful when the reaction does not involve a significant change in pH, or when the solution is too cloudy for a normal indicator to be seen. But spectrophotometric titration is just one of the many applications of UV visible spectroscopy. This technique also finds extensive use in the field of analytical chemistry. For instance, it's frequently used to quantify the concentration of a particular substance in a mixture. Whether it's a pharmaceutical sample or a water sample from a river, UV visible spectroscopy can help us determine what's in there. Furthermore, UV visible spectroscopy is integral to the study of molecular structures. By observing how a molecule absorbs light, scientists can glean valuable information about its electronic structure. This, in turn, can shed light on how the molecule behaves and interacts with other molecules. In the field of environmental science, UV visible spectroscopy is used to monitor air and water quality. It's instrumental in detecting contaminants like heavy metals in water or harmful gases in the air. The applications of UV visible spectroscopy are as diverse as they are numerous, encompassing sectors from medicine to environmental science, and even to the food and beverage industry. This brings us to the end of our exploration of UV visible spectroscopy. We've covered a lot of ground, but there's always more to learn. That's a wrap on UV visible spectroscopy. Today we've journeyed through its theory, explored Lambert's law, Woodward rule, and the fascinating world of photometry and spectrophotometry. We've delved into the intricacies of its instrumentation, tackled the complex analysis methods, and seen its practical applications. Remember, the beauty of UV visible spectroscopy lies in its ability to unveil the unseen, a tool invaluable for scientific research. Subscribe for more because you won't find me later. Keep exploring, keep learning.